Okay, we have retained our integral. This one's from the UNSW Integration Bee from 2023. This was round 2, problem 1. We have the integral of the sum from n equals 1 to infinity of 1 over n squared plus 4n plus 3 dx. Okay, to get started with this is actually much more of a series problem than it is an integral problem. So what I'm going to do is just kind of break this out and we'll just focus on this series and see what we can do to reduce this. Now, the first thing we can do is we can actually factor this. This numerator, that's actually going to factor. I can write this as n plus 3 times n plus 1 in the denominator. And then from here, what you could do to simplify this is you could actually do partial fractions. You could use the cover-up method on this. I like to kind of do it on the fly though, so what I'll do instead, which is really the same thing, is I'm actually we'll just keep the denominator here like this. And then what I can do is in the numerator, I'll just kind of create something. We'll do this as n plus 3 minus n plus 1. And I do that using these terms just because I know I'm going to get cancellation that way. The only trouble is when you put these together, the n's are going to cancel, but then we have 3 minus 1, this value is 2. So it's not the same as what we have over here, 1. Well, it's easy to fix that. What I can do is we'll just multiply by 1/2 in front, and now this here is exactly the same as this. So then I can take this and we can split this up into 2 fractions. Well, the first one's going to be this n plus 3 over n plus 3 times n plus 1. And then for the second one, we'll have a minus sign between. This will become n plus 1 over n plus 3, n plus 1. But then we get the cancellation here and here. So we have a 1 there, and the same thing here, cancellation, 1 in the numerator. And so then taking this, we'll put this back into our sum, but for the half, this is going to be a constant with no n. So I'll bring this in front of the summation like this. And then we'll have all this other stuff. This is going to become 1 over n plus 1 minus 1 over n plus 3. And now for this sum, we'll just keep our 1/2 in front. And now to get a sense of it, let's just kind of plug in some values starting at n equals to 1 and see what's happening. So first, when we plug in n equal to 1, this is going to give me 1/2 minus, this is going to become a 1/4 here. And then next, when n equals 2, then this is going to become 1 over 3 minus 1 over 5 here. And then we'll just do a few more. So this is going to become 1/4 minus 1 over 6. And of course, this is going to just keep going this way on and on to infinity. But then at this point, what you notice is we get a whole bunch of cancellation. Like first of all, we can cancel 1/4 with 1/4 here, 1/5 with 1/5 here, 1/6 here, 1/7. And then if we kept going, there's going to be terms down here in the middle somewhere that's going to cancel this 1/8 and 1/9. And eventually we'll have some terms at the end that don't cancel. The only thing is, because we're going to infinity, we can look at this as like a limit here. If we look at this here as the limit as n is going to infinity, well then this piece is going to 0, this piece is going to 0, and so we don't have to worry about this here. What we do have to worry about is these 2 terms up front that didn't cancel. We have this 1/2 here, we have a plus 1/3 here, and so what we can do is put this together and get our solution for this. So this is going to be, we're going to have a 1/2 in front, and then with this we'll get a common denominator. I can write this as 3 over 6 plus 1/3 I can write as 2 over 6. Putting this together, we have 5 over 6 times 1/2. That's just going to give me 5 over 12. But now that I've made a mess of the board, let's just take this value, plug it back into our integral, and we can finish it off. Okay, so now that we determined the value of our series is just 5 over 12, we just have a constant value. You could bring this up front of the integral, but now we can just integrate this, and what we're left with is our final solution of just 5 over 12 x plus c, and that's it. Okay, so there you have it, just telescoping series inside of an integral. Thanks everyone for watching. Have a good day.